Okay, we are very pleased to have Dr. Yifei Lou to give this week's 1W-MINDS seminar. Dr. Lou received her PhD in applied math from UCLA in 2010. After that, she joined the School of Electrical and Computer Engineering at Georgia Tech as a postdoctoral fellow. A year later, she had a joint position as a visiting lecturer at the Department of Mathematics, UCSD and UCLA. Since June 2012, she became a postdoc at the Department of Mathematics at UC Irvine. She was on the faculty in the Mathematics Science Department at the University of Texas, Dallas from 2014 to 2023, first as an assistant professor and then as an associate professor. Currently, she has been in a joint position in the Department of Mathematics and the School of Data Science and Society at the University of North Carolina at Chapel Hill. Her research interests include compressed sensing and its applications, image analysis, and numerical analysis and optimization algorithms. She is a recipient of a 2019 NSF Career Award. Now she has served as associate editor for the Journal of Inverse Problem and Imaging, some journal on image science, and the journal La Mathematica. Yifei, it's your turn.
Okay, thank you, Lucian, for your introduction, also advertising my talk. And also I'd like to thank the organizer of this 1 week maths seminar. I also benefit a lot from participating in this seminar. So today I'll be talking about several of my recent work on scale-invariant regularization for sparse signal and low-rank tensor recovery. Okay, so in addition to overview and conclusion, my talk will be divided into 3 parts: so theory, algorithm, and applications. So first of all, let's give a big overview of what the field I'm working on and then why I'm proposing such method. So although I guess everyone hear about this data science, big data, yes, big data is ubiquitous everywhere, but I think I usually call myself working in a small data region, in the sense that the data that we acquired or transmitted is often limited by some technical constraint. For example, here I show you a CT scan. So you know there is can you see my mouse? So there is an X-ray source, right? It passing through the human body and got detected on the other side. So in the real setting, it will be somewhere here, and it got projected or recorded on the other side. So the problem with a CT scan is that the X-ray radiation is harmful to human body. So therefore, in order to maintain the dosage within a safe limit, you cannot take as many as projection as you want. So we get a very undersampled scenario. And then what makes the problem even harder is this what called a limited angle scenario. So instead of 180 degree, you limited your scanning angle to say 45 degree. So you only see a portion of the data, and then you can expect the orthogonal direction, you kind of losing a lot of information, right? Because you know when you see orthogonal, you don't get anything out of that direction. So it's a underdetermined system. So mathematically, when we describe this small data scenario, is often formulated as this AX equal to B, where A is a matrix, X is a vector you want to solve, and then B is the data you obtain. So small data refer to that A has more columns than rows, right? And meaning that you have more unknown to solve compared to what you have. And then we all know from linear algebra that solving this AX equal to B with a fat matrix A, you get infinite many solutions. So in order to find the solution you want, you need to give me some prior knowledge so that I can, refine my solution space or guide my algorithm towards the desired solution that I want. So my research, not just this talk, most of my research focus on using sparsity, which assuming that this X has only a few non-zero element to well satisfy this AX equal to B. And then sparsity is a reasonable and useful assumption. First of all, it can compress, right? So instead of store this long, big vector, you can store a shorter version of the B, as long as you can recover X afterwards, right? So it give you a compression. And then in other words, it gives you some guidance regarding so that you can find and it's actually pretty reasonable in real life. As I said, in order to find a sparse solution, usually we rely on sparse promoting models. So the popular model is the straightforward way to enforce sparsity is what we call L0 norm, although it is not norm, but we just call it norm. So the L0 norm is counting how many non-zero element is in a signal. So if P is 0, right? So we should define 0 to the power of 0. In calculus, we know it's indeterminate form, but here we define 0 to the power of 0 is equal to 0. And if xj is not 0, we get 1. So it's basically if P is equal to 0, we're counting how many non-zero element, right? And then the P equal to 1 is the popular convex L1 norm. So L0 norm is NP hard, and we usually use the convex approximation to approximate the L0 norm. And actually, you can choose P in between, just that it's not norm, it's non-convex, right? And there are another two methods that can interpolate, in my opinion, between L0 and L1. So let me focus on this transform L1. So if A is equal to 0, so you get basically xj over xj. Again, you need to define 0 over 0 is 0, right? So this, if A is equal to 0, you get L0 norm. If xa goes to infinity, this transform L1 goes to L1. And then recently, I proposed this with my collaborator. We look at this error function from statistics. And this is actually, the definition from error function, right? So error function has the property that if this sigma goes to 0, it converts to a L0 norm. If sigma goes to infinity, it goes to the L1 norm. So I want to point out that these three models, they are somehow interpolating between L0 and L1 by properly choosing a parameter A, P, and sigma. And then all of them are what we call separable function, meaning that a function can be separate into different form on each particular argument, right? So I can plot a function with respect to each scalar. So remember that we want to approximate the L0 norm. L0 norm is basically this black curve, right? So it's equal to 0 at 0 and equal to 1 elsewhere. So this black curve is our goal. We want to approximate the L0 norm. And then the L1 norm is this blue curve, right? So it's the absolute value. And then, you can see that all those non-convex methods is somehow interpolating between L0 and L1. And you can expect why L1 doesn't work very well. You can see that if X is becoming large, then the difference between L1 and L0 become bigger and bigger. So you can expect if for large magnitude, L1 is not a good surrogate for the L0 norm. And then there's something in between. See, so I want to point out this error function does a pretty good job, approximating when X is very small to the L0 norm, right? But today my focus is not about all those separable functions, but actually towards a non-separable function, in the sense that I have L2 norm. So L2 norm without square, it's not separable, right? So I want to focus on this L1 over L2 norm, and then it is motivated by a Heuer measure that was proposed 20 years ago. So this is the definition for Heuer measure. This n is the dimension of this x. So you can see that no matter what dimension n is, no matter what is the magnitude of x, this Heuer measure always returns from 0 to 1, right? Because L1 over L2 is bounded between 1 and then root of n. So this Heuer measure is between 0 and 1. 1 meaning it's sparser. So here I give you 3 examples with different length, different magnitude. And then, it's all scaled down to, after looking at the Heuer, it's becoming, this is 0.95, 0.9, 0.8. So I want to say that sparsity is not always, you have to be something sparse. You can also allow to have small magnitude, as long as your energy is dominated by one or few elements. That vector is called sparse vector. So usually, a Heuer measure can be a good indicator of a vector whether it is sparse or not. So you can see the bigger the skewer, or closer the skewer measure to 1, the sparser the vector will look like, right? So basically, if you want to have sparser vector, you want to maximize the skewer measure. And it's a negative of L1 over L2, so it's equivalent to minimizing the L1 over L2. And this is what we're trying to do for. So I started working on L1 over L2 like 5 years ago. Okay. And then some advantages of L1 over L2 is that, first of all, it's scale invariant. I will give a definition in a few slides. It does not have model parameter. Unlike, LP, you need to choose P, TL1, you need to choose A, error function, you need to choose sigma, right? So L1 over L2, it's by itself, you don't need to choose parameter. And then lastly, another advantage, like we observed through experiment, is that the L1 over L2 is performing very good once X has a high dynamic range, meaning that the largest non-zero element divided by the smallest non-zero element is big. This probably because of its scale invariant, so it can deal with big change in your vector. Okay. And I also want to point out some disadvantage of the method. First of all, it's non-convex, non-linear, and it's non-separable. Like separable is defined to be, you can separate into different summations. So due to non-separable, numerically, it's posed a lot of challenges. So yeah. Okay, so I also want to extend the sparsity into a low rank, and so there's in between there's a low rank matrix, and then now I'm directly go to low rank tensor. So if you don't know about tensor, I hope everything you just consider its matrix form, just it's in high dimensional. So here, everyone knows about matrix SVD. So the tensor SVD is like this. You have, a 3D or higher dimensional tensor. It can be decomposed into two orthogonal tensor U and V, and then in the middle you have this every frontal slice. It is a diagonal matrix. So it's kind of a matrix version of singular value decomposition. Of course, I need to tell you how to define this product, how to define transpose. But unfortunately, I have to omit. Just go with me that this is matrix version of tensor SVD. Okay, so let me define some terms. So suppose I have a tensor, I can apply FFT along the tube, the 3D dimension to get a hat version. Okay, and then for the hat, it is also a 3D tensor or cube, and I call every frontal slice is x hat I. So notice that this x hat is a matrix, right? So I have all those matrices, and then we put them together to be a tensor. So I keep talking about low rank tensor. So unfortunately for tensor, there are different definitions for rank, and also it's depending on different matrix tensor product. So I will talk about two definitions for the rank. First, it's called average rank. By name, it just average the rank of each frontal slice after taking FFT. And there is another rank called the tuber rank. It's basically counting how many non-zero tube in your middle singular the singular value matrix or tensor. Okay, so apparently these two are different ranks, and then you can verify that the average rank is smaller than the tuber rank. Okay, so after the rank, I want to talk about some norms. So we can define a tensor Frobenius norm. So it's basically we can express Frobenius norm into the summing of all the singular value square among all those tubes. So this you can see there's a different version of the singular values, and you take the square, you sum them up. And then there's similar to nuclear norm, there's a tensor version of the nuclear norm. So basically, you're adding those singular values together because it's the singular values are all negative, so you don't need the absolute value, unlike the L1 norm. So we propose this tensor nuclear norm over Frobenius norm. So by name, it's just the tensor nuclear norm divided by the Frobenius norm. And if we stack all those sigma into a vector, this tensor T and F is the ratio between the L1 norm and then the L2 norm. So what I want to say is that I'm talking about L1 over L2, and it can deal with sparsity. And if we look at the tensor version, we can apply L1 over L2 on the singular values as a vector and to achieve a low rank approximation. Okay. So I want to talk about some theoretical properties for this L1 over L2 model. So since we just ended with tensor, so let's talk about some properties for this tensor nuclear norm over Frobenius norm properties. So this is what I meant by a scale invariant. So suppose I have a non-zero scalar C. After multiply this C with the tensor, after taking the TNF, it's the same as its original form. So this is what I call a scale invariant. And then the proof should be fairly easy, because if you multiply by C, you will have absolute value of C on the numerator and absolute value of C in the denominator. And then because C is not zero, they cancel out, right? So we have this property. Next is the unitary invariance, meaning that we can multiply this tensor with a orthogonal tensor on the left and on the right. It's the same tensor Frobenius norm. Yeah. And then the boundedness, so this TNF is bounded by some kind of dimension. Okay. So that's some to prove all of this, it's basically just cauchy squash inequality. Okay. And then here is some kind of more advanced property. Let me start with the matrix case, meaning that I want to apply L1 over L2 on the vector. While solving AX equal to B, right? So first of all, this NSP is a property for a matrix. So a matrix is called satisfy NSP of order S if for any vector belong to the kernel, the vector's L1 norm on the support is smaller than the rest of it on the non-support, or S bar refer to the complement. And then within this NSP condition, we can show that a S sparse vector is the unique solution to the L1 minimization. Okay, so sparsity at the sparse solution is actually the unique solution for the L1 solution, if and only if A satisfies this NSP. So in other words, NSP is a necessary and sufficient condition to guarantee that the L1 minimization will find you a sparse vector, right? Okay, so this is about the recovery of using L1 norm. Well, I want to do something with L1 over L2. So I want to see if I minimize L1 over L2 such that AX equal to B, what can I get? So the difficulty or the challenge with L1 over L2 is that it's non-convex and it's also non-separable, right? So a lot of analysis in L1 will break down. So I need a stronger assumption, which I call stronger NSP. And then the top one is the strong NSP, and then the bottom one is the original NSP. So the only difference is that here I need S plus 1, where S is somehow the sparsity level. And then here is just 1, right? 1 times this. So the reason why I call this a strong NSP is that if the matrix A satisfies the strong NSP, it automatically satisfies the original NSP. So in other words, this condition is stronger than the original NSP. Okay, and then within the strong NSP, we can prove that a sparse solution is a local minimizer of L1 over L2. In other words, so I have the feasible set, which is AX equal to B, and I can always find a V set in the kernel of A, so that X bar plus V is also satisfies AX equal to B, right? And then this V is bounded within a scalar. So in a small neighborhood of X, it is always the smallest value of L1 over L2 compared to its neighborhood. So in this sense, it is a local minimizer of L1 over L2 that also satisfies AX equal to B, right? So if we compare this result with the classical original NSP, there are a couple of differences. First of all, in original, it is if and only if, so it's necessary and sufficient. And then, so we are unfortunately only sufficient, right? If satisfied NSP, then we have the local minimizer. It's not the other way around. And then the other difference is that in the original, it says like the sparse solution is somehow a unique solution. But here we can only prove to be a local minimum. The reason is that L1 is a convex method, so global optimality is actually can be guaranteed, but here this is non-convex, so local minimizer is also actually a pretty good deal, right? Yeah, so that's I want to talk about the vector version of NSP, and then I want to extend similar thing into tensor. But when we move to tensor, we need to define somehow AX equal to B on the tensor version, right? So we need to discuss how do we take measurements, specifically linear measurements for tensor. So fortunately, we can achieve that by defining a m predefined tensor, A1 up to AM. And then for every measurement, I take the inner product between the vector, the tensor, and another tensor. So, you need to define the tensor product. But if you think about matrix version, it's just, you take the trace between two matrices, right? That will give you a measurement. So the low rank tensor recovery problem becomes you minimize the tuple rank and subject to, AX equal to B. So in vector version, it will be AX equal to B, but pronounced the same, right? Just different notation. NSP, the vector version, this NSP is applied on matrix. And now my next NSP on tensor is applied onto this linear operator A. Okay, so the tensor version of NSP states as follows. So for any tensor, if it's in the null space, I want the tensor nuclear norm of the first R singular values will be smaller than the remaining. Because singular values are sorted, right? So we only need to consider the first R versus the remaining. I don't need to do every support. So that's a little bit easier, but on the other hand, you need to look at the tensor version. Okay, and then I want to say this is the standard NSP in the matrix form, and then this parameter rho is just to make it's called stable NSP. Okay, and then this is our theory. So if this linear operator A satisfies NSP with rank R, and then we need some additional constraint on this rho parameter, then we can prove that for any low rank tensor, meaning the tensor with tuple rank R, and then also satisfy AX equal to B, is a local minimizer. So the conclusion for both vector version and then the tensor version are the same. Basically saying that if the linear operator satisfies NSP type of condition, then any sparse vector or any low rank tensor is a local minimizer of L1 over L2, subject to the linear constraint, right? And then the difference is that, for strong NSP, we have this additional S plus 1. And then for the tensor, we just need this rho parameter. It's actually aligned with the regular NSP condition. Yeah, so that is the theory part. Maybe I can pause here to see if anyone has questions. Shall I move on?
I had a quick question.
Yeah.
So the way that you define the null space property is you use non-strict inequality for the one norm along the support and the complement.
Yeah.
So I think the necessary and sufficient version of that condition is when it's strict inequality.
Oh, okay.
And I also believe that there's an equivalence, actually, at least over the reals, for the null space property with strict inequality and the existence of a constant satisfying the strong null space property that you put forward. So I'm just...
Yes, that's a good question. So I don't remember detail. I think so you think this is strict inequality, right?
Yes. I mean, I think that with non-strict inequality, it guarantees that the solution to the L1 minimization is sparse, but I don't think that it guarantees that it's unique.
Oh, okay.
I could be wrong.
So there may be some subtle difference regarding whether this is equality or strictly equality and whether this is unique or not. Yeah, you are right. I'll also be more clear on that. On top of that, I don't want to say wrong things. Yeah, unfortunately. But maybe for future reference, I'll be more careful on my slide. Thank you for this suggestion. Maybe I'll follow up with you later to make the correction. But I think what I put here is okay. Yeah, this is from my paper, so I'm pretty sure this should be fine. Yeah. Okay, shall I move on? Okay, so for the algorithm, I actually extended into a very general form. So remember, I want to do L1 over L2, so I can write in a general form of a function j over h. And then for some theoretical analysis, I further assume this j and h to be absolutely one homogeneous function, meaning that if you multiply alpha with your input, this alpha will be taken outside of j of u. So based on this property, and alpha can be 0. So meaning that we need to have j of 0 equal to 0. Okay, and then j of u should be always, oh yeah, there's no, yeah. So j of 0 is equal to 0. And somehow we need to define what if it's 0 over 0. So I think it doesn't matter we define 0 over 0 as 0. Okay. Yeah, so and then some application or some application for this general form, we can see I discussed L1 over L2. L1 over L2 both are absolute one homogeneous function. And then this is L1 over Sk, where Sk stands for the k largest, you're adding up k largest magnitude element of your vector. So notation is like U of k, parenthesis k. And then you can also prove that this Sk is also one homogeneous function. And then we can take gradient. So you get this is L1 over L2 on the gradient. So these three cases, they are all belong to the same, this j over h regularization. And then we consider least square just for simplicity. And then we can also extend this into be a more general data fitting term. Okay. So I want to give a few remarks before moving on. I guess maybe you hear about this Rayleigh quotient problem. So in classic linear algebra, if this L is a positive symmetric matrix, and this minimization is equivalent to finding eigenvalues and eigenvectors, right? And then if we generalize this into a general J and H, this becomes a linear Rayleigh quotient problem. So actually our motivation for L1 over L2 fits into this general Rayleigh quotient problem. And then I want to look at some literature regarding, how do we fit this framework. So remember, I want to do L1 over L2, right? And then such that, AX equal to B. So if we write AX equal to B, the feasible set as a omega, and then it becomes a nonlinear Rayleigh quotient problem. And then I want to say that most of the quotient problem, the algorithms need a constraint. Because what do? Is that they were first looking at the ratio. They were okay. So I think the standard fractional problem is like it only has a ratio. So actually this is the method came out last year. So they have L1. They want to do L1 over Sk, right? But they put this regularization on the numerator so that they can optimize they can linearize. They can make the quotient into difference and then update the ratio. So we want to do a quotient plus the data fitting term. So apparently it's easier to do quotient of sum like separately, but combine it's kind of difficult. So that's why later I will propose a method. Okay. Yeah. So first of all, let me talk about two things. First is about how do we solve the constraint minimization, and then we talk about how do we solve a quotient plus data fitting term as a combined objective function. So in my early work, I did realize that there's a relationship between the L1 over L2 and then the L1 minus L2. So if we define L1 minus alpha L2 and then we're changing alpha, And apparently there are relationship between this alpha and then the optimal alpha of this ratio model. And this relationship has been discovered in this paper. So basically it says that if you pick alpha, and if this objective function is larger than 0, then this alpha should be larger than your optimal alpha, and vice versa. So this theory actually suggests a binary search. So you just pick alpha, and then if you know the objective, let me just go to the pseudocode. So you pick a random alpha, and then you minimize L1 minus alpha L2, right? And if this objective function is negative, then the optimal ratio is smaller than this alpha. So you want to update your lower bound, right? And then, you know, if it's positive, you update, you update your upper bound, because lower bound is your optimal is larger than this alpha, right? So by doing this binary search, like in the end, you do, you know, you find the middle point, and then you do it again. So this is a very simple binary search based on this relationship. Okay, and then there are two problems with this algorithm. First is that it's very slow. Solving L1 minus alpha L2 is already very slow, not to mention you have to do this iteratively for many times until converge. And then second is that second is more critical in the sense that L1 minus L2 is also a non-convex problem. So minimizing this will not give you your numerical algorithm will not always guarantee to find a global optimal solution. Therefore, you know, you may end up with some suboptimal and stuck there. Okay, so where we cannot, so that's why I also propose two modifications. The first modification is that I have L1 minus alpha L2, right? So I linearize the L2 by, you know, a linear term, so that this whole thing becomes a linear function subject to a linear constraint. So this subproblem I can solve by linear programming, and then the solution can be guaranteed. And after I get solution, I just update my ratio, and I do it iteratively. So in this way, it will first, you know, it will speed up. You don't need to take the mean every time. You just take the ratio, optimal ratio. And second, this subproblem is a convex problem. In fact, it's a linear problem, right? And it's very efficient. But the problem with this approach is that this is linear, and then, you know, everything is linear, but linear programming can be no solution in the sense that this objective function can be unbounded. If it's unbounded, then, you know, argument does not give you a solution. It may return arbitrary, maybe return some garbage. So in order to add some regularization or you know, make it robust, I propose a second version just to add the quadratic term, so that, you know, it becomes there's a lower bound for the minimization, so that you can guarantee to find a next solution, and then you still take the optimal ratio. Okay, so theoretical guarantee for the this adaptive scheme is that, you know, first it's sufficient decreasing for the ratio, and then you know, this xk plus 1 and xk will go to 0. And then we can actually prove that if this x is bounded, the sequence will have a subsequence convergent to the critical point. I want to mention that the boundedness is actually important and it cannot be avoided, because L1 over L2 is not coercive, meaning that, you know, if one coefficient goes to infinity, you know, the entire L1 over L2 still is a finite. So there is no mechanism to prevent a coefficient go to infinity. So that's why in order for the convergence analysis, we somehow have to assume it is bounded, unless there are some other things can replace this boundedness, right? And then for the A1, because, you know, if beta equal to 0, we don't have the this lemma, so we can only show it has convergent sequence, but we cannot show a converge to where. Okay, yeah, so I guess I'll skip this, because this is another algorithm for minimizing L1 over L2. Basically, I have new variable for the numerator and then the new variable for the denominator, and then I do alternating direction of minimizers. Each variable has a closed form solution, so it will converge. When we compare, you know, all those methods, so remember I talked about 4 methods so far, right? One is the binary search, 2 adaptive schemes, and then 1 ADMM. So we find that, you know, ADMM, as I last method, it performs the worst. And then so this the first column is about the performance, is measured by success rate, and then the second column is the computation efficiency. So if we look at the performance, I would say binary search is the best, because if it works, it actually works pretty well. But binary search is the slowest method, as I explained. So the best method, the best efficient method, is this green, right, which is the A1, which use the linear programming to solve the subproblem. It's the most efficient way, but you know, performance-wise, sometimes good, sometimes it's bad. And a balanced method is this A2. It has, you know, it's somehow performance is good, computationally it's not that bad, and it has convergence analysis. Okay. So next I want to talk about the unconstrained minimization, where we use this ratio as a regularization, and then we add this data fidelity term. Okay. So we first try a very simple gradient descent. So basically you just, so this right hand side is the gradient descent. It's just simple calculus. But I do want to point out that we don't assuming J and then H, they are differentiable. So if J and H are not differentiable, we use subgradient. So that is the only difference than the standard calculus. Okay. So this is the gradient, and then I use a semi-implicit scheme. So on the right hand side, somewhere I use K, somewhere I use K plus 1. This is what I meant by semi-implicit scheme. Okay. And then we find that if I want to go from K to K plus 1, the solution of UK plus 1 is basically the minimizer of this following regularization. So this term goes to, so if you take derivative of the first term, you get this left-hand side, right? And if you take derivative with respect to U of the second term, you get this one. And then the derivative for J is your subgradient, and then the last term is the derivative for the least square term. So in other words, the UK plus 1 is the argument of minimizing this whole thing. Okay. And then we can solve. So you can expect if J of U is L1 type of method, so the rest are linear or quadratic. So with our knowledge, we should be able to solve this JU related subproblem, and then we do it iteratively. Okay. So I will not bore you with the algorithm, but I do want to share some mathematical analysis. So recall on the first line is our algorithm, and then we find it's easy to implement but difficult to analyze. So to get some mathematical analysis, we look at a slightly different term by replacing this denominator h at the UK to be a fully implicit, to be actual U. So that's the only change we make. Okay, and then we find this new implicit form will have this convergence analysis, meaning that UK plus 1 and UK will go to 0. And if UK is bounded, we get the convergence analysis. Okay, but all of this analysis is based on this modified scheme. But later we check numerically, we use this to implement, and then we still see some convergence, like numerically. But theory, we can only prove for the second term. Okay, and I also want to share some light regarding the boundedness. As I said previously, I said, you know, with L1 over L2, we have to assume some bound. But if we are assuming J and U are J and H, they are absolute one homogeneous, we can use this theory to guarantee the boundedness. So first of all, let me step back a little bit. So you may wonder what makes absolute one homogeneous so unique. Because you know the absolute one homogeneous function have these two properties. So the standard subgradient does not have this. But if J is absolute one homogeneous, they have this property that can help us to prove this convergence theory. Okay, and then we can also show that now back to the gradient flow. Okay, so if we can have initial condition AU is larger than the data F, then we can find that this gradient flow is actually decreasing. So therefore, if this flow is decreasing, then it's bound, that this U is bounded, right? So actually we find a sufficient condition for the uniform boundedness that required for this theory. And then the condition is that AU should be larger than the F norm. Okay, and then we actually verify for this theory. So I have plotted two cases. One is, the objective function is decreasing. Wait, it's not objective, it's the U that is decreasing. And this is the U is increasing. So if AU is below F, then we have, AU is below F, then we get U is decreasing. Wait, maybe there's some flip term. Anyway, so, sorry, I think that maybe I flipped the curve. So if it's larger than F, then it is decreasing. So maybe I flipped the curve. Sorry about that. But anyway, so we numerically verified that the theory actually holds. But I also want to say that this is a sufficient condition for decreasing. Although we do find, empirically, we do see it's sufficient and necessary, but this proof requires triangle inequality, so I don't think we can actually prove sufficient and then necessary. Okay. Okay, so for the remaining few minutes, I want to talk about some applications. So first of all is the limited angle CT reconstruction. So I want to say that first of all, image is not sparse, right? So if you look at these images, it has a lot of another element. So it's if you directly minimizing over L1 over L2, it doesn't work. But if you take the gradient of this image, and you can see that the non-zero element only occur along the boundaries and then all edges. So usually we are assuming edges or boundaries are of zero measure set compared to the entire domain. So we are assuming that the image after taking gradient will be a sparse signal. Okay, so that's why we will so we want to minimize the L0 norm of the gradient, and then by our technique we replace the L0 norm by L1 over L2. So that's why we have this term. Okay, and then this is the data fitting term. So this A corresponding to this linear projection, or it's somehow called random transformation. And then we also adding a box constraint. So as I said, we discussed a limited angle CT problem. In other words, our measurement is significantly less than what we want to recover. So the more constraint, more information we can introduce, it will help us better guide the solution towards what we want. So I know images always bounded between 0 and 1, so that's why we add this box constraint. And then there are some algorithms that we can solve to minimize this. And I want to say that these are two phantoms. This phantom that I put in the diagram is called shape-logan phantom. It is from MATLAB's command phantom, right? And this is another very popular phantom called full build. So later I just call FB. The difficulty for this phantom is that it has low contrast. So I make this window to be from 0 to 0.1, I guess, so that I can see these two circles and this ellipse. If I show it in a regular scale from 0 to 1, you will not see these two. You will not see those structures. So with low contrast, it's also imposing some difficulties when it comes to reconstruction. Okay, so that is the problem. And here is some result. So we first look at no noise, and with different scanning angle. As I said, we don't scan the entire 180 degree, but rather we scan 30, 45, 60. And then this FB is more difficult to recover compared to a shape-logan, so we need to acquire more larger angle so that we can expect a decent recovery. So I want to say the first column is the SART. It's a conventional method that is developed early 80s. And then this is L1, it's like L1 norm of the gradient, and this is L1 over L2 of the gradient. So this is PSNR and the relative error. So you can see that this is always, it's like the relative error is between like 1%. You can not see it visual difference. And L1 and the traditional method is like making 0.5% of the mistake, right? And then the L1 is much better compared to the classical method, but it's not as good as the new method. Next, let me show you some visual comparison. So this is the noisy case, and then on the top it is the shape logan, on the bottom it is the FB phantom. So the scanning angle is 135, so I bet it is about this much. So you can see that this region, and then also the opposite side, because it's symmetric, we get pretty good recovery. But the orthogonal direction, the recovery is actually pretty bad, because there's a lot of information that has been lost. Okay, so I think this has some noise. And then in L1 over L2 give you a decent recovery of the boundaries, and the inside it has some drawback, but with this only this much information, I think that the performance is much better. At least it's filling these boundaries, right? And then for the more challenging phantom, I think we pass through these boundaries, and also the inside is better compared. Well, at least we see these two circles here. Okay, so I want to say that this is a very challenging case. Next is a MI reconstruction. So how MI work is that you have an image, and then you take FFT, and then you only sample data along those radical lines. So that is one scenario. Of course, in real practice, they have different way to take the measurement. Sometimes they may also have the spiral scan. But here, for to generate my experiment, I just do radical lines, and I believe here there are seven lines here, which equivalent to 4% of the data that is sampled. So you can see it's significantly undersampled. And if you patch everything that you didn't acquire by 0 and take that IFFT, you get something like this. It's basically you cannot see any. You can see some rough structure, and then you also see some striking artifacts, right? And then this is the L1, just the L1 norm, and this is the L1 minus L2, and then L1 over L2. It's pretty decent. Again, it gives you a very good boundaries, just some kind of artifact along here and then here. The relative error is also much better compared to its these two methods. Okay. Here is a noisy case. So I want to say that this is a comparison between, it's the same model. So both of them, we are using L1 over L2. And then the middle column is using the ADMM. I didn't talk about it, but you just imagine there's some method before this quotient model. And then, we compare the quotient with a previous method. So I want to say that both these two columns are solving the same model, but using different algorithm. And then the quotient model, and then both of them are of the same complexity. Basically, they're solving the L1 type of method iteratively. And the quotient model clearly improves the performance of the previous model. And I think the advantage is that it uses some kind of a continuation from the gradient and make algorithm more stable. The ADMM, it's like jumping around. Maybe that's why it's not performing so well. But that are all my intuitions. I don't have theory to guarantee. Yeah. Okay. So lastly, I'll talk about tensor completion. So as I said, I want to use TNF. Let me remind you, this is a tensor nuclear norm over Frobenius norm, subject to some we only sample tensor on a set, which is this omega. So if the index is on omega, it agree with this matrix. Oh, sorry, it should be tensor, and then set the rest into 0. Okay. So I will make this constraint into an indicator function, and then I will introduce another tensor to apply ADMM. Again, the detail I don't know. I will not. I don't have time to describe. So let me first show you some results. So here there are 6 plots. They're about success rates. The x-axis is the rank, the tuple rank. The y-axis will be the sampling ratio, like 1%, 2%, and then 90%. So and each entry or each block is a success rate over 10 trials, I think. And then if the reconstructed solution by those methods to the ground truth is smaller than 10 to negative 3, we think this trial is successful, and then we compute the success rate over 10 trials. So the more white, it means the method is better, right? The more white, the better. So I compare with some existing method. So TNN is a tensor nuclear norm. It is a convex model. And then the remaining 3, 4, they are non-convex method. I don't want to bore you with your name, but just listing their they are all recent work. And then this is our method. It's under revision. Hopefully it will be published in next year or maybe later. But yeah, so you can see that we do have more white compared to the previous method. The next one is this, I think the iterative tensor nuclear norm. And then yeah, I'm plotting this diagonal line just for you to see that how much close it's to the diagonal line, so that you see more white or less white, right? And then we also look at some color image in painting. So color image is a RGB, right? So you can regard it as a cube, and then artificially blob adding some text color onto the figure. So you can see that. So this TNN may have some artifacts remains after denoising. So you can see A, B, C, D, and then our method has faded with those artifacts. I still see some A, B, C, D, but it's lighter compared to the other. A more obvious comparison is in this striking lines. So you can see TNN has a lot of lines. It's still, our method has a line, but it's lighter. That's all I want to say. Okay, so I think it's time for me to conclude. We propose a scale invariant L1 over L2. So ideally just one model, right? So if you just apply it to a vector, it becomes it will enforcing a vector into to be sparse. If you apply L1 over L2 onto the singular values of a tensor, you will we enforce a low rank tensor. And then for both models, we establish a low rank, a sparse is a local minimizer, right? And a low rank is a local minimizer for the tensor model. So that is our theory. Numerically, we propose a semi-implicit scheme. For the general quotient model, we offer some numerical insights on the convergence and then solution boundedness. And then finally, we show experiment that proposed approaches give better results in, I show city reconstruction, MRI reconstruction, and a color image in painting problem. Yeah, so that's all I want to say. Thank you for your attention.